Alrighty, folks, it's me again, Mr. Hess, back to teach you another lesson. Today is going to cover lesson 1.3 in our textbook. And the title of this lesson is Polygons and Other Figures in the Plane. Okay, so we're going to be testing out your knowledge of polygons today. Okay, so let's get things started then, first of all, with what is a polygon. And to be a polygon, let me adjust my picture here. To be a polygon, first of all, it has to be a closed figure. So a polygon is going to be a closed, I should say it's a closed two-dimensional, so 2D figure. Okay, and it is made up of segments that are joined only at their endpoints. So closed 2D figure made up of segments joined only at their endpoints. And in fact, specifically, you could only join one segment with two other segments, one at each endpoint. Okay, so basically like this. This is an example of a polygon. This is an example of a polygon. Even this is an example of a polygon. Those are all polygons. Okay, so polygons should have sides or segments. Okay, those are the sides of the polygon. Okay, and where they're joined only at their endpoints, that's called the vertices, or vertex is singular, but vertices is plural. Okay, so every polygon then has, for example, like there's a side, and then the sides meet each other at the what you might say is the corner of the polygon. That's more specifically known then as the vertex. Okay, so these are all examples of what is a polygon. I also want to specify while we're looking at this, let's take a look at what is not a polygon. Okay, and there's three things really you have to watch out for. It's not going to be a polygon if one of these three things happens. Okay, the first of those three would be this scenario. When you look at this shape that I'm starting to draw here, that's not a polygon. Okay, I hope it's obvious on this one what makes that not a polygon. After all, we said it was made up of segments joined only at their endpoints. And this one, as you can see, has a curve. You can't have any curves in a polygon. Okay, here's the next thing to watch out for. This is not considered to be a polygon. And if I just stop there, let's say. Okay, do you see the problem with this one is, like we specified up here, a polygon has to be a closed figure, and as you can see, this has an opening in it. Okay, so if it's open like that, it's not a polygon. And then there's one more thing to watch out for that would make it not a polygon. And that would be a scenario like this, where maybe I'm starting to draw along here, and even though that makes a kind of a neat looking fish shape, it is not a polygon. The problem being is that the sides or segments that make up a polygon should be joined only at their endpoints. And if you look right in here, okay, the side length we were drawing here that went across there and then went across here. See how they cross each other right in the middle? Okay, you can't have that happen. You can't have your sides cross each other. Okay, they should only be, again, intersecting at their endpoints, like up here. So if any of those three happen, that would make it not a polygon. So that's really all you need to watch out for. Everything else should be a polygon. All right, so that's what a polygon is. Now let's take a look at how you would name a polygon. Give me a sec here to clear up some space on my board. Alright, so if I have a polygon, for example, like this one, okay, and then each of these vertices, let's say, is labeled with, some capital letters like we've talked about before. A, B, C, D, E. Okay, now, when you go to name this polygon, all we're going to do is we're going to cram all the letters together to give it its name. But as you do that, it does have to be as you trace your way around the figure. So most people, when they look at this one, would just call it A, B, C, D, E. As you can see, it wraps back around to A again to start with. Okay, so you could write it like that. You could just say, okay, it's polygon A, B, C, D, E. Okay, or you could start at a different letter instead of starting at A. You could even go a different direction. So instead of calling it A, B, C, D, E, maybe you start at A and go the other way. Maybe you call it A, E, D, C, B. Okay, or like I said, you could start at a different letter to begin with altogether. Maybe you want to start at C. And then if you go, let's say, clockwise around it, we would have C, D, E, A, B. C, D, E, A, B. So technically, like this polygon that I have up here, which has 1, 2, 3, 4, 5 vertices, that means that there's technically 10 different ways to say it. Because I could start at any one vertex and I could go clockwise or counterclockwise. So there's 2 A's starting with A, there's 2 A's starting with B, there's 2 A's starting with C, and so on. So 2, 4, 6, 8, 10. There should be 10 total ways to say the name of this. So I'm just going to put an etc. there, rather than listing all 10 of those. Okay, you can't just randomly jump to any vertex you want on these. Okay, so you can't call this A, D, E, B, C. That's all over the place. It does have to trace around the perimeter of the polygon as you're naming it. Okay, so I explained what a polygon is. Now I explained how you name a polygon. The next thing I want to do is show you different classifications. How we would classify a polygon. So classifying polygons. Okay, I'm going to make a little table here out of this. And over here is going to be the number of sides. And over here then is the name of the type of polygon. Now, the least amount of sides that a polygon can have, you may have figured out, is 3. There's no way you can have a closed figure. Polygons have to be closed figures. You can't have a closed figure with less than 3 sides. Of course, you're familiar with that one. If it has 3 sides, we call it a triangle. Okay, the names make sense. Tri meaning 3, angle meaning angle. So it's a figure of 3 angles, triangle. If it has 4 sides, okay, now we're going to use, instead of tri, we're going to use the prefix for 4, which you should already, I hope, know, is quad. So this is called a quadrilateral. Okay, be careful when I say name a figure that has 4 sides, you know, or give the classification of a figure with 4 sides. A lot of people will tell me, oh, it's a rectangle or it's a square. You know, be careful. Yes, those are types of quadrilaterals, but you're being too specific when you say rectangle or square. So anything that's got 4 sides is what we call a quadrilateral. If it has 5 sides, okay, again, we were looking for the prefix. Tri was 3, quad was 4. For 5, the prefix for that is penta. So a pentagon is what we call a 5-sided figure. Let's see, is that what this was? 1, 2, 3, 4, 5. Yes. So technically, that's a pentagon that has 5 sides. Okay, the usual pentagon building that you might be familiar with is our defense building. United States Defense Building is the Pentagon, and it literally is in the shape of a pentagon. It's got all equal sides on it. You know, it looks something like that. Okay, and the reason it's literally got 5 different walls to it instead of your normal 4 like you see in buildings is because the Pentagon is one of our defense buildings, and there are 5 branches of our armed forces. You know, you got the Army, Navy, Air Force, Marines, and everybody always forgets that last one. And the last one is the Coast Guard. The Coast Guard is an armed force, believe it or not. So that's why they have the Pentagon literally shaped like that, where each one of these sides of the building is a different branch of our armed forces. You know, that might be the Army branch right there, for example. You know, that one might be the Navy, and so on. All right, that gets us up to 6. 6 sides. If it has 6 sides, do you know the prefix for 6? It is hexa. So this would be a hexagon. That's a pretty easy one to remember if you correlate it with the idea that many people know, and we're getting close to Halloween. The number of the beast is 666, and so 6 is often considered an evil number, and so 6, its prefix hex is easy to remember as well. If you think of when you put a curse on someone, they call it a hex. When you put a curse on someone, so just think, 6 being an evil number supposedly. So hexagon. As you notice now, a lot of these from here on out have this agon on the end, okay? So when we get up to 7 sides, yes, it does have its own special name that we can give it. And this prefix, again, does mean 7, okay? And technically there's a couple of prefixes that mean 7. There's one of them is septa, but we're going to use a variation of that yet with an H instead of a heptagon. So with an H, hepta means 7, and so does septa with an S. Okay, I don't know if you realize this, but September used to be the 7th month. October used to be the 8th month. November used to be the 9th month. December used to be the 10th month. There used to only be 10 months in our calendar until the Romans came over and got a hold of our calendar. They added 2 months. Okay, they squeezed 2 extra months into our calendar. But you don't know which 2 months. They're named after famous emperors, one of which is July. Yeah, July. The month of July is named after Julius Caesar. And then the other one that the Romans added in, again named after another famous emperor, August. Yes, Augustus was one of the emperors of Roman times, and they named August after him. So July and August, never used to be in the calendar, so it all makes sense if you take them back out. If you take those 2 months out, a lot of the names make sense for the months. Now they don't make any sense though after adding those in. So as we just mentioned a second ago, October used to be the 8th month, so 8 would be a octagon. Just like an octopus has 8 legs. Okay, I'm going to give you a few more of these yet. A 9-sided figure. Okay, and by the way, make sure you get these into your notes. Your textbook only goes up to 6, but I want you to learn a few more of these yet. Okay, but a 9-sided figure is what we call a nonagon. N-O-N-A, nana. Okay, nana, or even with a V here instead of the N, nova, are prefixes that are used to mean 9. These are all Latin-based names, by the way. So November, like I said earlier, used to be the 9th month. Okay, but this, when in our name here, nonagon has N-O-N-A, nana. 10, well, this is an easy one to remember. 10 years is known as a decade, so deca means 10, so a decagon is a 10-sided figure. All right, so at 10, I'm going to cut this off now. Although there are a couple more that you could use if you really wanted, if you really got up that high at least. You know, if it has 11 sides, they call it, instead of a decagon, it's called a decagon, where or like uno in Spanish means 1. You know, means 1. So 1 plus 10 would be 11, right? So decagon is 11, and then if you went to 12, it would be a dodecagon, where do means 2, and then deca is 10. So 2 plus 10 is 12. Okay, but after 12, there's really no other special names left. In fact, anything higher than 12 at that point, where it has any number of sides, I'm just going to put n number of sides where it would be, where it would be any number of sides. Okay, then all you do is throw a gon on the end of it, and there you got your answer for how you would label that. So if a polygon had, 25 sides, we would call it a 25agon. If it had 30 sides, we would call it a 30agon, and so on. Okay, so that's our classifications of polygons. All right, now there's one more term I want to cover here on polygons that you might run into, and that'd be what they call a regular polygon. Regular polygon. Now, regular polygons are often, if I said draw a, and then, insert polygon in the statement here, draw a hexagon, for example. Most people, when you tell them draw a hexagon, they're actually going to draw what's called a regular hexagon, because it's kind of human nature, it's in our minds to just want to draw a regular polygon versus something that's irregular. Okay? A regular hexagon, for example, would look like this. You'd have a picture like that right there. Okay, there's your regular hexagon. Whereas an irregular hexagon might look like this. 1, 2, 3, 4, 5, 6. There. That's an irregular hexagon. It has 6 sides though. These are both hexagons. See that? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, you can see clearly though, this one on the left here probably looks more appealing to you, because a regular polygon by definition, is going to have all sides that are the same length, so all equal side lengths, whereas this one over here did not necessarily have equal lengths. And on top of it, it has to also have all equal angles as well. So all of these angles should be the same as well for it to be truly a regular polygon. So a regular polygon has all equal sides and angles. All equal sides and angles. So, you are probably already familiar with some regular polygons. For example, a regular quadrilateral. If I said, okay, draw a regular quadrilateral. The quadrilateral has 4 sides. So if all 4 of those sides are equal and all 4 of the angles are equal, well, look what you get. 1, 2, 3, 4 equal sides and 4 equal angles. You get a square. See that? So a square is a type of regular polygon. If I said draw a regular triangle, many of you might recognize that as well. It would have all equal sides, all equal angles. Okay, many of you know that as a equilateral triangle because it has all equal sides. But by the way, that would also be known as equiangular. It's got all equal angles as well. So those are some common shapes that again, you've probably already seen before. Okay, but if it's going to be a regular polygon, it should have all equal sides and all equal angles. Okay. Let's see. The next thing I want to talk about, since we're concentrating on polygons in this lesson today, is area of some of these polygons. Okay, so some common shapes that we'll be able to work with here is the triangle. The rectangle is another one that we're going to take a look at its area. And finally, the last shape that comes in handy when finding area is what we would call a trapezoid. All right, a triangle you should already be familiar with. You know that a triangle looks something like this. 3 sides. Okay, if you ever want to find its area, the area of a triangle, to find its area at least, you have to know 2 measurements. You need to know that how long the base of the triangle is. Okay, so we need one side of it, so to speak, you might say. And the base doesn't have to be on the bottom. You can move the base around wherever you need to. But the other measurement you need to find the area of this triangle is also the height. Okay, now the height of the triangle should always be at a right angle to the base. So I'm going to draw it in another color like that. Okay, so our formula then is half of the base times the height. Okay, and I'm going to pause my video here so I get a manipulative. Alright, so I've got a manipulative here for us, something to help you visualize this. And before I explain how this formula came about for a triangle, I want you to take a look at this shape here, which is a parallelogram. Okay, and a parallelogram, we're going to derive its formula for its area as well. We could throw it on our list of areas here, but to show you where it comes from, we first, of course, have to focus on the rectangle. Now, the rectangle is one of the first shapes that anybody learns about. You know that rectangle gets its name from the fact that if you've looked at the name, it says right angle in it basically. So it has right angles, you know, at each of these corners here. Okay, but For a rectangle, the formula is often written like this, where it's length times width. Or some places, again, sticking with this theme of base and height, might call that base along the bottom and that height along there. So L times W or B times H, base times height. Turns out in a parallelogram, we're going to need the base along the bottom and a height at a right angle. So again, I'm going to put that height in there in pink like we did here, just to emphasize that this height here has to be at a right angle to the base. Okay, if you're wondering where they come up with this formula then of base times height for the area of the parallelogram, let me work a little, what I'm going to call a little math magic. Okay, if you take a look, I've got my parallelogram pictured here. And if I were to cut along this height, okay, now if I just take the two pieces and interchange them, you'll see it fits back together, and you can see it makes a rectangle. Okay, so if this were the rectangle we were finding the area of, you'd be taking this width here and this length here times each other. Okay, well, this width along here you can see is the height of the original parallelogram, and this length along the bottom really didn't change any. All I did was take this piece right here and move it on this side of it. So the length along the entire bottom along here is still the same. Okay, so instead of length times width, it's base times height, where the base and height are at a right angle to each other for a parallelogram. All right, now I could go back to our triangle and explain where this formula came from as well. Okay, you'll notice that it's almost the same formula as a parallelogram, only they have that 1/2 in there. Okay, so just to kind of show you why it's only a half of a parallelogram, well, I've got a picture then here again. I made a little manipulative of a triangle. And I want to show you then that if I were to make a copy of this triangle, so I'm going to copy the vertices there like that. Okay, so there's a copy of that triangle. The reason I made a copy of it is because I want to take this triangle, I'm going to rotate it, and if I attach it right back to this side along here, do you see that that triangle and this triangle together make a parallelogram, just like we had there? So if the parallelogram was base times height, each of these triangles is exactly half of that parallelogram, so they're half base times height. Okay, so that's where that formula comes from then for an area of a triangle. Now there's one more shape, the trapezoid. Okay, this is an example of a trapezoid. To be a trapezoid, the only thing that needs to be true is that the top and bottom here and here, those need to be parallel. Okay, it doesn't really have to be the top and bottom. You could turn it sideways. That's still a parallelogram. But basically what I'm trying to say is one pair of opposite sides are parallel, but only one pair. That's why it's not a parallelogram. I like to say it's only half of a parallelogram. It's only got one pair of parallel sides, not two. Okay, so other than that, with just exactly one pair of parallel sides, that's what's going to make it a trapezoid. Now, how do we find the area of a trapezoid? Well, let me draw a picture of one here that we can refer to, and then give you the formula here. Okay, once again, just like in our other shapes that I've mentioned up here, we are going to use a base and a height, okay? And that height, by the way, does have to be at a right angle. So right along here from one parallel side to the other, if you measure this at a right angle like this, from one parallel side to the other, that's what we call the height of the trapezoid. And on a trapezoid, though, technically, instead of one base, it actually has two. The two that are parallel. You know, remember this top and this bottom here are parallel, right? So one of them we're going to call B1 for base 1, and the other one we're going to call B2 for base 2. Okay, and you need those three measurements in order to find the area of a trapezoid, because it turns out that our formula, well, let's see if you can figure out the formula. I'm going to, again, work a little math magic here to see if you can figure it out yourself. Okay, one of the first things I did, I don't know if you can see that on there, there's a crease for a fold right there. What I did was I folded it so that the two bases met up at the bottom here. They were equal. Okay, and then what I want to do was, since I folded it there, I'm going to cut right along that fold. All right. So let's see if I can work my math magic here again. Okay, here's the original trapezoid. There, that's a better view of it. Okay, and as you can see, I cut it right through the middle like this, so that now I'll be able to take this one piece on the top, rotate it, and attach it right here. And notice now it's going to make one big long parallelogram again, which remember was base times height. Okay, so if we take a look at this one, let's start out with the height of it. Look at the height of this parallelogram. How do you think this height here compares to the original height of the trapezoid? I hope you're looking at this and saying, oh look, it's half, Mr. Hess. That's only half of what the whole height right there is. Okay, so that's the start of our formula. In fact, area of a trapezoid is half the height. Okay, and then we're going to take that times, you remember this was base times height for a parallelogram. Well, our height was half of the height of the trapezoid. Our base of this, the length all the way along here, all the way along that bottom, is going to be, now again, if I rotate this, do you see that the base that was up here gets rotated down to the bottom? So it's that upper base that was up here, and it's the lower base over here. Okay, see it? I still got my lower base here, my upper base at the top. When I rotate, upper base is down here with the bottom base. So we're going to add those two together. We're going to take the B1, the B2, and add them. Notice I put it in parentheses, meaning you do have to add those first. Then you start doing your multiplying. All right, so that's our formulas then for area of those shapes here that I covered. That'll come in handy here when we start to do some problems. And before we jump into a problem here, I do want to mention that if the shape you're trying to find the area of looks very irregular, you know, awkward shape, a weird shape, you know, maybe something like this. Let's say you're trying to find the area of something like that. Okay, now we have a postulate, and if you remember correctly, I talked about this in a previous lesson. A postulate is something that we cannot prove, but we know it's true. Okay? So we do have a postulate here called the area addition postulate, which says then that we can take a region like this and we can break it down into smaller parts, find the area of the individual smaller parts, and then add it all back together. Okay, so something like this, I might do something like this. You could do something like where if you cut this across here, now do you see you have a triangle? Okay, you got, like I'll call that region A and this one region B. Okay, you could find those two individual areas now. You can find the area of this triangle, and what do you suppose this is if I cut that straight across and it's parallel to that? Yep, you guessed it, that's a trapezoid. So you can find the area of the triangle and the trapezoid separately and then add them back together to get your total area. Okay, or if you don't think you cut that up enough, you know, you're welcome to do something like this where you even cut it up some more. Now you'd have, well, if I called this B, this C, and this D. Okay, now I'd have area of a triangle here for A, area of another triangle for B. C looks like it's a rectangle here. And then D is another triangle. So you could do that even. You could find the area of all those individual pieces and then add them all up to get the total area. Okay, we're going to apply that concept here on our next problem. And on our next problem here, it's also going to introduce a term that gets used occasionally in geometry, and that is population density. Population density. So population density is exactly what it sounds like. It's how many people they pack into a small area. You know, the population density, for example, in Marion County is not very high. We've got a lot of farmland in Marion, so there's not very many people per square mile. Okay, but if you were to go to New York City, for example, where everybody's living in apartments and they live in multiple story homes, then you got a lot of people packed into a small area, so they would have a lot higher population density. You know, it'd be a lot more dense, a lot more people per square mile in a big city like New York. Okay, so let's try a problem that involves population density and at the same time is going to incorporate the idea that we were talking about here with the polygons and finding area. Okay, if you ever want to find population density, I would make sure you get this in your notes, by the way. You figure out the population density by using a very simple formula. You're just going to take however many people you have and you're going to divide it by the area that you're squeezing those people into. Okay, your area then should be in square units, by the way. I forgot to mention that on all my formulas there that I just gave you. Those are all formulas for area, and area is always in square units. You're literally finding how many little 1 by 1 square blocks, you might say, fit inside of an object. Okay, but it's as simple as that. Population density is people divided by the area that you have those people in. Okay, so for this next problem, I'm going to see if I can flip around my camera here, and I wanted to show you, well, here's the original problem. They've got this island called Bird Island, okay, and they show you, they got a little scale at the bottom. See the little, there it is, a little scale that shows you that 1,000 feet would be that distance in gray. Okay, and one of the things they mention in this problem is they mention that there it is, 1,058 birds, okay, currently populating this island. So we want to figure out the population density. We want to figure out, instead of people, how many birds per square foot, because they have this all in feet, as I can see here. So we're going to figure out how many birds per square feet there are. Okay, now in the next picture I'm about to show you, now you see they took that island and they represented the island with some shapes that are pretty close to the same shape as what the island originally was. It's not going to be perfect, okay? We're trying to estimate a little bit here. Okay, so they came up with these shapes, and I'm going to try to duplicate those same shapes up here on my board. Okay, so I'm going to start with that rectangular shape, the B in the middle here. Okay, as I look at this, I count there's 1, 2, 3, 4, 5, 6, 7 blocks across. And if we go down, 1, 2, 3, 4, 5, 6, 6.5, it looks like down. It's almost a square. So yes, 7 by 6.5. Okay, so I'm going to do the same thing on my board here. I'm going to make a 7 by 6.5 going down this way. Okay, there's my center square that matches what they did there. Okay, now off to the side over here is a triangle, and off to this side is another triangle. Let's go back to this one over here. When I look at it closely, I figure out that one of the sides along here is 1, 2, 3, 4.5. Okay, so it starts out attached to that rectangle, and it looks something like that, where that length is 4.5 from there to there. So 4.5 there. Okay, and one other thing that I'm going to measure on here, I know that if I'm going to have to find the area of that triangle, that I'm going to have a base times height and a half in the formula, half base times height. So I need that base and height to be at a right angle to each other. Okay, so I don't know if you can, well, you don't need to visualize it if I show you right here. If I'm going to call this my base of this triangle, okay, then I'm going to run a height. I'm going to run a height out here. Okay, and that's going to be my height. So like if I turn this like this now, see it? Now I'm using this as my base, and my height is outside of the triangle there. That's still at a right angle to that base. Okay, now when I go back to my picture, I can figure that out. It would be attached right there at that vertex, and it would go 1, 2, 3, 4 units to get back to that line, see, across there. So I know that this is 4. Okay, you still with me here? And then I got one last shape. I got another triangle here. This one just seems to be a nice right triangle. It goes 1, 2, 3, 4, 5 units out that way. And it even goes down at a right angle down straight down this way. 1, 2, 3, 4.5, let's say. So I've got 5 out that way, and it meets down here at 4.5. All right, so there's the big picture again of what we got going on here. Okay, I'm going to move my back around again. There we go. Okay. Now let's do the math here. Okay, we need to figure out if we're going to find out the population density, we're going to need to find the area. So I'm going to find the area of my regions. You know, we had in our picture that was region A, this was region B, and this was region C. Okay, so if I want to find the area of A, it's a triangle. I'm going to follow my formula, half base times height for region A. This is for region A. So I'd have, and like I said, I'm going to call this my base so that this is at a right angle to it. So my base is 4.5, my height at a right angle to this. You see if I extend that out, see how that's at a right angle to that. Okay, that height is 4. So the area of region A is, well, let's see, half of 4 is 2. 2 times 4.5 is 9. Okay, so the area of that region is going to be 9. Now let's move on to region B. In region B, we have a rectangle. It's a 7 by 6.5. Okay, so for region B, we're using length times width. Okay, and our length is 7, our width is 6.5. Okay, if we take 7 times 6.5, let's see, what does that give you? It'd be 42 plus 3.5, so that's 45.5. All right, and then region C. Region C is another triangle again. So again, we're going to use this formula, half base times height. This one's a little easier. This time the right angle is right there. So we can use 5 and 4.5 as our base and height since they're already at a right angle. So 5 we're going to call our base. Our height is going to be 4.5. Okay, now, let's see here. I better grab a calculator. It's starting to get hard to do in my head. So if I take half of 5 times 4.5, that gives me 11.25 for that part. Okay, now the area of the whole thing would be A plus B plus C, so 9 plus 45.5 plus 11.25. Okay, that gives us a total area then of 65.75. Okay, that would be our okay, one last thing too on this. That's per block. Okay, I did all this so far is square blocks. Okay, I want to take you back to my picture. And I want to show you then. Okay, 1, 2, 3, 4, 5 blocks make up 1,000 feet. That means then that each block should be what, 200 feet? Because you'd have 200 plus another 200 would be 400, would be 600, 800, 1,000. So each of those blocks is 200 feet. Okay, this is how many square blocks I had. Okay, so a square block would be 200 by 200. Okay, there's a square block, 200 by 200, which then if you found out it's the area of the square, it would just be then you'd multiply those. So that would be 40,000 square feet. Okay, in that area, in one little block. So we're going to take this answer, 65.75. We're going to multiply it times 40,000 square feet. And that's going to be our square footage. Okay, so 65.75, we're going to multiply times 40,000. Okay, here we go. 65.75 times 40,000. Okay, the area that we get for this is 263, and then 4 zeros, 1, 2, 3, 4. So it'd actually be 2,630,000 square feet. Okay, now don't forget earlier I pointed out that the problem said that there was 1,058 birds. So we're finally ready to find our population density. All we have to do is divide this out, and that'll tell you that how many birds there are per square foot. So if we divide that out, 1,058 divided by 2,630,000 comes out to, well, 0.000402 blah blah blah. So as you can see, every bird has plenty of square footage on that island. Okay, because there's not even close to one bird per square foot, much less, 0.0004. So plenty of square footage then to be roaming around for those birds. Okay, but that's population density. So if you ever want to know then how dense the population is somewhere, you take the people, divide it by the area. Okay, the hard part here was finding all this area. Okay, other than that, you just got to divide them out. One of the last things here in this lesson that I want to cover is one of the most famous theorems in all of geometry. Many of you have already used this theorem before, so I'm hoping this will be a quick review, and that is the Pythagorean theorem. Okay, this one is a theorem, not a postulate, meaning we can prove it. Okay, and if you want to see one such proof of it, in your textbook on page 25, they actually show you, why that theorem actually works. They have a proof that involves some pictures even. Okay, but I'm just going to go ahead and cover the basics here. You know the theorem looks like this: a squared plus b squared equals c squared. But more importantly, you need to understand that the Pythagorean theorem only applies to right triangles. Okay, it's got to be a triangle with a right angle in it, a right triangle. Okay, and in fact, then on this formula, the A, B, and C are certain parts on our picture here. In fact, C is the most important one, the one that's over here by itself in the formula. It's this side right here, which is known as the hypotenuse. The hypotenuse is always located right directly across from the right angle. And because it's across from the right angle, it will also be the side that is the longest. Okay, so your hypotenuse is always across from the right angle, and it's always the longest side. The other two sides are both referred to as legs. That's a leg, that's a leg. Okay, and they're labeled as A and B. The legs then will be at a right angle to each other. Okay, but the only one that's across from the right angle is the hypotenuse. There's our formula. All you have to do then is be able to, of course, make use of this formula by plugging in what you know and solving for the one thing you don't know. Okay, so this works great if you have one missing length out of the three. So let's give you a scenario here. Let's say that you got a house and you've got this ladder and you're leaning this ladder against the house. Okay, and ladders come in certain sizes, you know. Let's say that that is a 20-foot ladder. Okay, so if I say, okay, that's a 20-foot ladder, and let's say that the bottom of the ladder here, let's say that I already know it's a certain distance away from the house. Okay, when I set up my ladder, let's say that this distance away from the house then is 7 feet. I want to know then how high up the house can you actually reach with your ladder. So I want to know then how long is this side right here of our, as you can see here, of our right triangle. Okay, so on a problem like that, okay, make sure then that, I always say, look for your hypotenuse right away. Make sure you're getting that one plugged in correctly. Okay, your hypotenuse should always be across from the right angle. So across from the right angle in this case is our 20. And then if you get that one correct, the other two you really can't go wrong with. On the legs, you're welcome to interchange them any way you like along here for A and B. So X and 7 are our A and B. So when I plug those in, our equation now looks like this. We got X squared plus 7 squared equals 20 squared. Okay, the next thing I would do is go ahead and do some of the squaring. We're just going to simplify. That's 49, 7 times 7, and 20 times 20 is 400. Okay, and from here, it's really just simple algebra. I want to get the X by itself, right? So that means I need to get rid of the 49. I would subtract 49 from both sides. So now I'd have X squared equals 351. Okay, and then there is one last step here. This is something that we haven't done yet in geometry so far that I've had you, is a problem with exponents. Okay, we have one finally with exponents. Remember when I was teaching you that all of algebra is really just the order of operations, only we're doing it backwards? And I told you the one exception was that the P, the parentheses, still comes first. So instead of PEMDAS, it's PSADME. Okay, and as we worked our way along through the problem here, we got rid of, we didn't have any parentheses. We did our adding and subtracting. Like here, I subtracted a 49 from both sides. Okay, there really was no multiplying or dividing to do on this one. So I'm actually up to this. I'm up to the E, the exponent part. So now that's the last step whenever you're solving equations, is to get rid of that exponent. And to get rid of it again, just like anything else in algebra, we have to do the opposite. And the opposite of squaring is what we call a square root. But whatever we do to one side, we're going to have to do to the other. Now the square root of x squared is just going to be x. We're going to have our answer here in a little bit. But we have to use a calculator to get it here, because square root of 351 I don't think is going to come out to a nice whole number for us. And more often than not in the Pythagorean theorem, it does not come out to whole numbers. But it can. There's a chance it might. Let's see what we get here. Let's see. Square root of 351 is a decimal. It's approximately and this is the symbol for approximately. I don't know if you ever knew this. If you make your equal sign have like a little wave in it, it's like you're saying, it's about, so it's about 18.73, somewhere in that range. Yeah, I'm rounding. It was 18.734994. Okay, so that's the Pythagorean theorem. And again, I'm guessing you've probably used it before. That's probably a review for you. Okay, it does solve slightly differently though if it's actually the hypotenuse that you're trying to find. Maybe we should throw one of those in there real quick, and then I'll call it a day here. Let's try the same problem, only this time. Let's say that I've got a triangle. You can make up your own word problem that goes with it, but let's say this time we're trying to find this side, the hypotenuse, knowing that, let's say this side is 15 and this side is 6. Okay, so this time you'd make sure the x, since it's the hypotenuse across from the right angle, it would go in for your C. 15 and 6 would go in for the legs, A and B. 15 squared is 225. 6 squared is 36. Now here's where it's a little bit different. If you remember on the last problem, there was a 49 I had to subtract over. Okay, not in this case. See how the x is already by itself on that side? Well, just go ahead and take these two then and add them. So if you add 225 and 36, what is that? 261. And then, just like our last problem, get rid of the square by doing the opposite, the square root. So the square root of 261 would be our answer. If you want that in decimal form, that's approximately 16.155. If you round that, it'd be 16.16. It's about that much, approximately. Okay, so there you have it. There's your Pythagorean theorem problems. And I think I've taught you everything you're going to need to know to do your homework. So I'm going to go ahead and end this video, and you can go ahead and work on the homework.